Let's look at phosphorus pentachloride. Phosphorus pentachloride contains one phosphorus atom bonded to 5 chlorines. When we look at our chlorines, they have 4 effective pairs around their atom. They have 1 bonding pair and 4 lone pairs. And we know that when we have 4 effective pairs around a central atom, that atom needs to have an sp3 hybridization. But if we look at phosphorus, phosphorus has 5 effective pairs around its central atom. It's got that trigonal bipyramidal molecular geometry. So if we need 5 orbitals around phosphorus in order to make this structure, we're going to have to incorporate d orbitals into our hybridization. So in this case, we're going to have d sp3 hybridization on our p orbital. The s, 3p, and 1d orbital are going to become 5 equivalent hybridized orbitals. So if we look here, we've got our phosphorus. Those orbitals have hybridized into 5 equivalent d sp3 orbitals. So our chlorine, sp3 hybridization because we need 4 effective pairs. So when we look over on the left-hand ball and stick model there, we've got our central phosphorus surrounded by our 5 chlorines. And if we look over on the right-hand side, now we can see that each of our chlorines is sp3 hybridized. 3 of those hybrid orbitals are going to contain lone pairs of electrons. One of those hybridized orbitals is going to overlap with a d sp3 hybridized orbital from phosphorus and form a sigma bond. So we're going to end up with 5 sigma bonds between phosphorus and each of our chlorines in our phosphorus pentachloride model. If we look at sulfur hexafluoride, we're going to have a structure that looks like this. If we look at each of our fluorines, they have 4 effective pairs. So we're going to need sp3 hybridization on each of our fluorines. Sulfur has 6 pairs of electrons bonded to each fluorine. So again, we're going to have d orbitals involved in our hybridization. So this time we're going to have d2 sp3 hybridization taking place in our central s orbital in our molecule. So 2 d orbitals, 1 s, and 3 p orbitals are going to meld together to give us 6 equivalent d to sp3 hybrid orbitals. So again, if we were to look at that sulfur now, we're going to have 6 orbitals that are all the same that would give us that octahedral electron geometry. So when we summarize this localized electron model, the first thing we do is we draw our Lewis structure. We decide how many valence electrons there are on each atom in our molecule. We draw our molecule so that our octet or duet rule is fulfilled. Any extra electrons we would add onto the central atom and expand the octet into the d orbital. Then from there, we would look at each of the atoms in the molecule. We would decide where the electrons are using our Vesper structures, determine what the molecular geometry will be, and then we would specify the hybridization that takes place on each of our atoms. So let's summarize. If we've got 2 effective pairs, we're going to have sp hybridization, and that's going to give us a linear arrangement. If we have 3 effective pairs, we're going to have sp2 hybridization, and that's going to give us a trigonal planar arrangement. If we have 4 effective pairs, we're going to have sp3 hybridization, which will give us a tetrahedral arrangement. If we've got 5 effective pairs, we'll have d sp3 hybridization, which will give us a trigonal bipyramidal electron geometry. And if we have 6 effective pairs around the central atom, we will need D2sp3 hybridization, which would give us that octahedral arrangement.